Everyone, welcome to Practical Mechanics. I'm Mohsen. In this video, I'm going to talk about geometric tolerance perpendicularity that apply to external feature of size or a shaft. I draw the object, perspective of the object, and front view, top view. Then, and apply, we wanted to apply and interpret the perpendicularity tolerance pointed to that is applied to the axis of this shaft here, which must be perpendicular to the datum A, the bottom surface as datum A. If there is nothing here in front, it means that this tolerance applied at RFS. RFS means regardless of feature of size. It means that tolerance doesn't depend on the actual size of the part, actual size of the shaft. It doesn't matter you produce it 30.2 or 29.9 or 29.8 or 30.1, always the geometric tolerance is the same. Let's show it with some actual mating envelope from MMC to LMC. MMC for this shaft is 30.2. Then other size 30.1, 30, 29.9. LMC, least material conditions, minimum material of the shaft is at size 29.8. LMC size. And geometric tolerance at RFS is 0.2, 0.2, 0.2, 0.2, 0.2. It means that there may be millions of sizes between these from 30.2 to 29.8. I just show some of them. And for all sizes, perpendicularity error is equal to 0.2. What does it mean? It means that the axis of this shaft must lie inside a narrow cylinder, consider three-dimensional, inside a narrow cylinder, and that narrow cylinder must be perpendicular to datum A, not the axis. It's not possible to produce an axis that is perpendicular to a surface in production. It's not possible. Then the designer consider an allowance for this error of production and say that, okay, if that is called axis interpretation. If the axis is inside a narrow cylinder, then the part will be accepted. Maybe the axis is like that. As long as it is inside the narrow cylinder, it is acceptable. Then zone shape here is cylindrical. Zone size here is fixed 0.2. And the only modifier that we use at these conditions is phi modifier here. RFS means no M, no L, no P, actually. You can use P as well here, but nothing is in the front, not for RFS. For other cases that apply M or L modifier. Okay, that's the case of RFS. Zone shape is a narrow cylinder. Axis interpretation is required. You must actually verify the axis, that this axis lie inside the narrow cylinder or no. If it lies inside that, is acceptable. What about other modifier? We can use M L, P modifier as well when the perpendicularity for external feature of size. I continue this table for M modifier. Assume that we have M modifier. M modifier means that the goal of assembly, goal of the production is assembly. The goal is assembly. First, M means the goal of the production of this part is assembly. Two, at MMC, geometric tolerance is 0.2. 3, bonus tolerance is permitted. 4, functional gauge may be used. Actually, surface interpretation in this case, or outer boundary or surface interpretation, we can use a functional gauge. And the functional gauge here is a ring gauge for the shaft. And just check it, that it can sit well inside the whole gauge, actually. Okay, then let's consider it virtual condition to surface boundary interpretation. We have virtual conditions here. When we have an M modifier, we have a bonus tolerance and total geometric tolerance as well. At MMC size 30.2, it says that you must use only 0.2, not more, no bonus. Total 0.2. When you depart from the MMC size, how much is departure? 0.1. That's a bonus. Manufacturer gave the designer gave this value. Okay, if you produce at a smaller size, the difference between a smaller size and MMC size is a bonus. You can have more error. 0.1 here, 0.3. You can have 0.3 error when you produce at 30.1. And so 0.4, 0.5, 0.6. What does it mean? It means that if you produce the shaft at a smaller size, you can have 0.6 error. Here the goal is assembly. The shaft can be more bended or oblique in this case when it is smaller, because it can go easily inside the hole, can be assembled. But when it is at the larger size, you cannot have more than 0.2. And it makes the boundary of the shaft how much? 30.4. A shaft with size 30.2 with 0.2 error in perpendicularity is like a shaft with size 30.4. And the size of the hole that it can be assembled with the mating part must be 30.4 at least. Otherwise, it cannot be assembled. This is why you have to calculate virtual condition size, which is 30.4 mm. If it works, the other sizes will work, no problem. That's our worst case scenario here, or outer boundary for this. This is if you use a gauge for that one, for example, that's it, and use a gauge or ring gauge, something like this. Then this size should be 30.4. And the part, if you put here, the ring here, it goes, go gauge, part will be accepted. Otherwise, it opted for scrap or to rework, to fix it or correct it. If it is possible. That's for L modifier. What happened? If instead of L modifier, they use L modifier. If they use L modifier, it means that at LMC, you must have only 0.2 error, not more. And this 2 will be changed. 0 bonus, 0.2 total. And Y, in this case, the goal of the design is not assembly. It's not made assembly. Designer is worried about the strength of the pin or the shaft. Is it strong enough and doesn't break or fracture during service life? Is the material that it contains is sufficient? When the point is strength of the part, in this case, they consider L modifier. They wanted to say to manufacturer, if you produce at 29.8, which is the narrowest, smallest, and actually smallest diameter for the part, you cannot have more than 0.2 error. Why? Because when it must be corrected, for example, to make it perfect vertical, we have to remove the material from it. And it is, how much will be this? 29.6. If you cut it to fix it, to make it exactly 90 degrees angle, not for assembly, then you have to remove the material, the meat of the metal from outside surface in order to correct it, the angle, 90 degrees angle. In this case, you make it thinner. Actually, you make it thinner, you make it weaker. Designer want to make sure that at 29.8, there is no more than 0.2 error, because 29.6 can solve the answer the design, but less than that, no. This is why the table is different. This is point actually 1, it should be 0.3, this is 0.2, 0.4, this is 0.3, 0.5, this is 0.4, 0.6. It means that manufacturer, if you produce at 30.2, you can have 0.6 error. Since if we remove 0.6 error to fix it, for example, still there is sufficient material inside this shaft that protect it from fracture. We talk about this L modifier and talk about everything else in the other video. We just wanted to focus on the perpendicularity that apply at the RFS and MMC to external feature of size, which is a shaft. Thank you for watching. See you in the next video.